Hi, welcome to our final segment that has to do with Chapter 1. In this portion, I will be going over unit conversions, and then there's a quick thing about temperature and about density and specific gravity. So we'll be wrapping it up this way. The techniques I'm going to show you for unit conversion will match those in the book. It's the method that I prefer using. However, for some of you, it may just not click. You may have had learned all of this using proportions for so long that trying to learn a new method now is just not going to work for you. With that in mind, I will do a separate video showing you how to solve these same problems using proportions. You have to pick one way or the other. The reason for that is the way that I will first show you using, you can call it the factor label method or dimensional analysis. Here, they're listed right here on the page. This method involves multiplying fractions. The other method, using proportions, you use an equal sign between them and solve for x. So they have two different formats and they have two strategies, different strategies for solving. If you mix them together, you're going to have a lot of trouble with the problems. The early part will be the same, where you decide which two numbers and units will go together in one fraction. That will be constant no matter which method you use to solve it. After that, though, once you've taken a look at this method that I'll show you first and decide whether or not you can commit to it, and that will be the way you'll use from now on. If you decide not to do that, then you can check out the proportions video. You will be able to solve the problems that way. It's just a lot slower. So here we go. I've now created a third handout. I spent time between my last recording and this to try to set it up. Oh, actually, no. Oh, heck, I don't know. This one's called Chapter 1, Part 2B. Yes, so it must be the third one. And I've labeled it unit conversions, temperature, and density. And so feel free to look for this on Moodle. And I don't know that there's anything to fill in the blanks here, but you should see that this would be much cheaper and easier for you to print out than trying to print out all the slides. Okay, the next thing we're going to do is take a look at the rest of the Chapter 1 PowerPoint. I'm going to use this little function. This is a shortcut down here to starting the slideshow on the current slide. There we go. And here's what we're doing. We're going to solve problems with different units. There are different names for the technique we will study that makes changing from one unit to another simple and accurate. The examples of names for this are factor label method, dimensional analysis. I'll typically end up just calling it unit conversion. The other method I would use, I'll call like unit conversion with proportions. This does not use proportions. Conversion factors. These are used to convert a quantity with one unit into a quantity with another unit. I call these my gateways between units. We'll start with an original quantity. This is going to be a number and a unit that we don't want any longer. It'll be the one given in the problem where it's, say, in pounds and you need to get into kilograms. You'll then use this conversion factor, which I'll give you more information about soon. By multiplying, you will end up with the desired quantity with the desired unit. Conversion factors are usually written as equalities. That's because these values will go together. 2.21 pounds is the same as 1 kilogram. These two units are joined together with those two numbers. 2.21 next to the pound symbol, 1 next to the kilogram symbol. To use them in the unit conversions, whether you're using the factor label method or you're using the proportions method, you need to write these values as fractions. You want to keep units together. Personally, I prefer to have the two different units in the same fraction. So perhaps I would choose to put pounds on top and then put kilograms on the bottom. With what we're going to be doing here with factor label method, then we have rules about which guy goes on top and which one goes on the bottom. Note though that I read this exactly the same way. 2.21 pounds is equal to 1 kilogram, or the fraction on the right, 1 kilogram equals 2.21 pounds. Same thing. It's very tiny lettering down here. I guess it was an afterthought of mine, but I want to make sure that you know that many conversion factors are defined quantities. They do not affect the number of significant figures in the answer. So all those ones with the metric conversions where there are 1,000 milliliters in 1 liter, that does not affect, it looks like it's only one significant figure, but in reality, it's an infinite number. And in this case, even though it's 1 kilogram, that's a 1 with an infinite number of significant figures or zeros after it. And the 2.21 pounds, we're just going to count that as an unlimited number as well, meaning ignore these when you're trying to figure out the number of significant figures for your answer. The majority of the time, we're just going to use whatever the number was that was given in the problem that we're trying to get away from. You'll see how it works. Here's the neat thing about units. We can treat them like numbers. They cancel out. Do I have an example here? I do not. If I asked you what is 5 divided by 5, well, if you've been reviewing your fractions anytime, hopefully you'll know that that's 1. For example, if I had 5 slices of pizza and 5 people, each person would get 1 slice. We can do the same thing when it comes to units. We can take, say, centimeters, divide it with centimeters, and we'll be left with an invisible 1. Centimeters can cancel out with centimeters by dividing them. With our conversion factors and taking advantage of the idea that I can cancel units out by dividing, I'm able to get rid of any units I don't want anymore as I work towards the unit I do. We'll end with the desired unit and go, hooray! So here's an example. To convert 65 kilograms into pounds, we're going to start with the original quantity, 65 kilograms. In almost every problem I'll give you, you're going to have a number with 1 unit. Then you'll have extra information that involves 2 units. Right now, we're starting with the number that has only 1 unit, just kilograms. We're going to use a conversion factor to get out of kilograms and into pounds. Well, we have one, if not memorized, then we have one on the sheet, I believe it's page 12 of the textbook, or I suppose you could Google it online. Note though that whenever you search for these things online, 2 things will happen. Number 1, you may be given a different conversion factor than what we're using in the lecture and what's in your book. Number 2, because I'll be trying to make sure that you can do 2-step conversions, which I'll be showing you how to do soon, I don't want you trying to skip a step. I know that you can use the internet now and go, say, directly from kilograms to ounces. But because for some people this course is counting as a math requirement, there will be times where I'm going to tell you that I want you to go from kilograms to pounds first and then into ounces. Now it can all be in one long calculation, but I'm not going to want you to look up any conversion factors that I haven't given to you. Okay? All right. So again, there should be a table with useful conversion factors at the back of your book and or on page 12. I'll be honest with you, these pages may not be correct. These may be from an earlier version, and right now my copy of the new version is at the ACC library for any students who didn't have access to the ebook yet. So with that in mind, I can't correct these pages, but it should be around page 12. I'll also be putting up a copy somewhere. I mean, on Moodle, I'll find something to give you guys that has the values in it. All right, here we go. So 65 kilograms. We have two choices. We can either put kilograms on top and pounds on the bottom, or we can put pounds on top and kilograms on the bottom. The deal is when you are multiplying fractions, you multiply across the top and then you multiply separately the numbers on the bottom. That's what you would have been taught at school earlier. Here's what I'm going to teach you. You multiply the numbers across the top and you divide by any numbers on the bottom. Multiply across the top, divide by numbers on the bottom, and by their units. We're going to want the one with the kilograms on the bottom because then I get to do kilograms divided by kilograms. That will cancel out and equal 1, just like 5 divided by 5 is 1. The pounds are left alone. There's nobody there to cancel out the pounds, so we will be in the unit that we wanted to end with, our desired unit. Calculator says 143.65, and then the unit that we're left with is usually the one on the top right. The top right-hand side will be the desired unit, the pounds. Okay, do we get to stop here? No. We started with 65 kilograms. How many significant figures does that have? Just 2. If you don't know the answer to that, please go back and watch the previous video, the chapter 1, part 2 measurement video, and that will review the idea of significant figures with you. There's also a handout that I've worked hard on and posted onto Moodle as well to help you practice some more with using significant figures. Okay, we did multiplication and division. The rule is that we can have in our answer the same number of significant figures as the fewest number in our original measurements. Now the 2.21 and the 1 kilogram, we're going to ignore those. Those are standard values. But the 65, with its 2 significant figures, tells us that our answer can only have 2 significant figures. I'll start with the 1 on the left, and then I'll decide what to do with the 4. The 4 could stay a 4 or round up to 5. There's a 3 next door. The 3, he's less than 5, so I'm going to just keep it as 1, 4. Now that would give me 14 pounds. That's not the same as 143 pounds. Our final answer needs to be 140 pounds. The 0 at the end is not significant because there's no decimal drawn in. No decimal, the zeros at the end don't count. They're placeholders. They're important, but they're not significant figures. I want you to always arrange your conversion factors so that the denominator in one term cancels out the numerator in the preceding term. Let's do this again together. Say we want to know how many liters of blood are in 1.0 pints, or 1 pint. All right, so we have our original quantity, the one that has only one unit. We're trying to get into liters. We would use a chart, and in this case, I see. So the information will be given. We have to use 2 conversion factors. How exciting. We'll have 2 pints equal to 1 quart and 1.06 quarts equal to 1 liter. In this case, I'm working with 3 units, pints, quarts, and liters. I've got 5 numbers. The number from the original problem that we're trying to get rid of, then the 2, the 1, the 1.06, and another 1. This lets me know that I'm going to have to do 2 steps. If I use proportions, I'm going to have to do 2 separate proportions. If I use the factor label method, I can do it all in 1 step. But again, there'll still be an extra 2 fractions involved. The 2 pints equal to 1 quart can be written in 2 different ways, with pints on top and quart on the bottom, or quarts on top, and pints on the bottom. This guy the same way. What are the 2 ways? Quart on top. What's the other way that I could write this equality? This information as a conversion factor. I could put liters on top and 1.06 quarts on the bottom. How will I know which ones I want to use? It's all going to be about which unit I want to cancel out. The unit I want to cancel out will go on the bottom. We're going to cancel out the pints first. They gave us pints, we didn't want pints, so we'll put pints on the bottom. Note that that's going to put us in terms of quarts, because the quarts are getting canceled out. Well, if I want to get rid of quarts and go to liters, I better put quarts on the bottom of the next conversion factor. I'm going to draw it all out for you now. So we do 1.0 point, and I always say times in a line, times in a line. And on the bottom, we'll put the 2 pints, and on top, we'll put the 1 quart. The pints will now cancel out because I'm dividing. When 1's on the top left here, you could put it over 1 if you want to. He's on top, he's on the bottom. They divide and cancel out. Then, to get rid of quarts, I put the quart on the bottom, liter on the top, quart divided by quart, they cancel out. They become an invisible 1. I'm left with just liters on the top right-hand side. Well, that's great. We wanted liters for our answer. And where did that number come from? Okay, I'm going to have to do this by hand pretty soon because this is all just kind of throwing it out there for you. This came from multiplying across the top. 1 times 1 times 1. Hopefully you didn't put that in your calculator. When you multiply or divide by 1, the number doesn't change. So, save yourself some time. But I then need to do 1 divided by 2 divided by 1.06. We're going to divide by anybody on the bottom. I know this is different than how you were taught to do fractions and multiplications. I know they told you to do it as 2 separate steps, well, 3 steps. Multiply across the top, multiply across the bottom, then find the answer that you had on top and divide it by the answer that you found for the bottom. Whew, it's exhausting. Or you could just multiply across the top and divide by all the numbers on the bottom. The answer with the correct number of significant figures. We do that because our answers cannot have more accuracy than the original quantities. 1.0, there's a decimal, so the 0 at the end was significant. 2 significant figures, my answer has 2 significant figures. The zeros at the beginning of the number don't count. He has an important job. He's letting us know there's a decimal coming up. So it's not 47, but 0.47, but he's not a significant figure. All right, let me see what else I have. Okay, before we do this, I'm going to switch over for a second to Alt-Shift-S. I'm going to switch over now to my DocCam, and I'm going to do some more problems with you guys. Here it comes. Wait for it. There we go. All right. Okay. Let's do a 1-step one and then a 2-step one. We know, how about we know 1 pound is equal to 16 ounces. Can you see that okay? Does that help any? Nope, that made it worse. Okay. And one more try. Let's try this. 1 pound equals 16 ounces. Then, let's say I want to know how many ounces are in 3.30 pounds. Wow, you really can't see that at all, can you? Okay, let's try this. There we go. And let me make it clear again. All right, now we're talking. Okay, how many ounces are in 3.30 pounds? We have 2 units, pounds and ounces, and this is the number in units that we're trying to get rid of. These 2 units will go together in a conversion factor. I'm going to start with this information, 3.30, and the pounds times an allowing. To get rid of this unit, I need to put it down here on the bottom. Numbers kind of freak me out, so I'm just going to start with the units first. The pound will go on the bottom, and then the information we have is to convert it into ounces. So ounces will go on top. My final answer is ounces, so I can go ahead and stop here. I don't need to do another conversion factor. We're going to stick our numbers to the units. In this case, the 16 will stay with ounces, and the 1 will stay with pounds. In the calculator, we're going to do 3.3, because you really don't need the 0 there, times 16. If it was something other than 1, I would divide by 1. But I don't really need to do that because the number won't change. And what's this going to come out to be? 8 carry the 1. You guys are doing it while I'm doing this, right? Okay, Google, what is 3.3 times 16? 52.8. Excellent. 52.8, and I love it because we have some interesting information. Are we going to pay attention to these numbers here for significant figures? No, these are standard numbers. We ignore these. How about this number, 3.30? There is a decimal point, so the 0 at the end is significant. This has 3 significant figures. My answer also has 3 significant figures. So my final answer, 3.30 pounds, is the same as 52.8 ounces. And that makes sense to me. There's a lot of little ounces making up a larger pound, so I expect to have a larger number for this small stuff. Let's do another one now. Let's do, wish I had one that had some other numbers to it. Okay, the centimeters to yards, there we go. We have, let's say we have 573 centimeters equals a certain number of yards. And I'm going to give you 1 inch is equal to 2.54 centimeters, and 1 yard is equal to 36 inches. This is one I do with my TEAS students, getting them ready to take the TEAS exam to get into nursing school. All right. This is going to have to be done in 2 steps. I know that because I've got 2 equalities here, 2 items to use for my unit conversions. The number with 1 unit that we're starting with needs to be written down first, 573 centimeters, times and a line. For me, this is a game. Boy, the recording speed is a lot slower. Okay, so it's a game. We're going to play the units game. The centimeters needs to go on the bottom of the next fraction. This unit comes down here. I don't have a way to go directly into yards. I do, however, have a friend in common. Centimeter is buddies with inches, and inches are buddies with yard. So let's go into inches first. Before I put in the numbers, to me, putting the numbers in is like putting on the brakes. I'm going to keep going. I'm going to take care of my units first, and then I'll plug in numbers. So I do another times in a line, and I record that the inches that I don't want for my final answer are going to go on the bottom of the next fraction. Then on top, I have a way to go from inches to yards, so I'm going to put yards on top. If you want, you can go boom, 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 and cancel all those out and realize that you're just left with yards for your answer. Now that I've finished working with all the units, I can go back in and plug in the numbers. With the inches to centimeters, this is the only information I can use. Don't use the 36 inches yet. That has to go into the fraction that has to deal with yards. In this one, the 1 inch goes on top. The 2.54 centimeters goes on the bottom. My numbers stick to their units. You won't always have a 1 on the bottom. In fact, here we go again. The 1 will stay with yard. The 36 will stick with the inches. In your calculator, rather than taking the time to multiply across the top, multiply across the bottom, then get the number from the top and divide it by the bottom, this is all you have to do. 573. We don't need to do times 1 times 1. That would not change the answer. Instead, we're going to do divided by 2.54 and divided by 36. Do you see how much faster that is than doing the whole multiplication on top, multiplication on bottom, and dividing? It's also less likely of having typos. Every time I have to type in an old value into my calculator, not only is it time consuming, but it also leads to errors, or at least more opportunities for errors. No clue what this comes out to be. Well, let's find out. I assume it's going to be a pretty tiny number because yards are so much bigger than centimeters. 573 divided by 2.54 divided by 36 equals. Oh, I got a wicked long number, 6.2664, blah, 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 blah. Okay. So I went from 573 down to 6. That's what I would expect. What should we do now? All right, these guys are standard values. I'm not going to worry about those. 573 has 3 sig figs. That means I'm going to keep the 6. I'm going to keep the point. I'm also going to keep the 2. For my third significant figure, I need to look next door. 6 is 5 or more, so I will round up. I'll add 1 to that 6. My final answer then, 573 centimeters is the same as 6.27 yards. Divide, divide, divide by anyone on the bottom. This is going to be the hardest I'm going to give you for unit conversions. In a more advanced chemistry course, I mean, I've done ones that were five across. They had 4 or 5 different conversion factors involved. But the toughest ones I'm going to give you guys this semester is where you have to go through 2 unit conversions. Most of them are going to be just 1 unit conversion like we did up here. But we'll be using all kinds of interesting units. First, we'll get all this stupid American stuff out of the way, but we will also be converting between the things like curies and millicuries. And okay, that's probably the coolest one, but we'll work with those when we talk about radiation in chapter 10. All right, so what else do I want to tell you? There are 2 ways to teach you how to convert between metric units. For now, I'm going to show you the way that you can use with the same factor label method. Then in that separate video, when I talk about proportions, I will also show you another technique where you write out the prefixes. So the KHD, and then the base units and so on for all the prefixes like kilo and hecta, and then you move the decimal point around. That takes just a little bit longer, but for some folks, again, especially the ones that just really are not able to do the factor label method, that will be a way that will be familiar to a lot of people. So I will do that in a separate video. For now, let me just show you again. If we know that there are 1,000 milliliters in 1 liter, then I can say if I have, I don't know, 360.0 milliliters, how many liters is that? Again, we have 2 units, and we technically have 3 numbers here. Using the factor label method, we would start with the 360.0 milliliters times in a line, put the milliliters on the bottom, and the liters on top. Once I write down that 360.0, I never write it down again. That was it. I didn't do that up here either. I wrote down the 573, that was it. The ones that go in this conversion factor have to be the ones that are equal to each other or are related to each other. In this case, it's the 1 liter and the 1,000 milliliters. In my calculator, I'll probably just do 360 divided by 1,000 because I don't need to put in 0.0. It's not necessary. Okay, and what that's going to give me on my calculator is 0.36. My calculator doesn't do scientific notation. So let's see what we're going to do with this. Let me recopy that for a second. We have 360.0 milliliters. We got out of milliliters and into liters by putting 1,000 next to the milliliters and 1. Remember, the way I do it, which is a little different than the book. Well, actually, it's not. I think the book did start doing it this way. 1,000 little milliliters. The big guy gets the 1. This was 360 divided by 1,000, and it gave us 0.36 on the calculator. This number here has a decimal. The zeros at the end are significant. This has 4 significant figures. These don't count, they're a definition. This right here has only 2 significant figures. Well, that's not going to work. I'm doing multiplication and division. I need the same total number as the total number in this number. Okay, so thanks to that decimal, and if it wasn't there, I would put it down at the end of the number, I can now add on 2 more zeros at the end. These are significant because there's a decimal. This now has 4 significant figures. This now tells me that 360.0 milliliters is the same as 0.3600 liters. Hey, let's play a game. What is this in scientific notation? If you want to pause the recording and give it a try, that would be groovy. Then you can come back and join me in solving the problem. Here we go. The rule is, step 1, put 1 number in front of the decimal. It's going to be the guy that's the farthest to the left. So in this case, it's going to be 3 point. Then the next thing will be write the remaining significant figures. In this problem, that's going to be 3.600. Step 3, write times 10. Step 4, your exponent is positive if the original number was greater than 1. That doesn't work for us. 0.3600, this guy starts with the decimal. It's less than 1. Okay, that means we need a negative exponent. Step 5, the exponent number, wow, I really spelled that one wrong. Exponent number equals the number of places we moved the decimal. Well, originally it was 0.3600, and we moved it 1 spot to get it behind the 3. So our final answer then is 3.600 times 10 to the negative 1. And I do have to write the 1 there. Can't have an invisible 1 when it comes to scientific notation. Now here's the interesting part. We didn't talk about this before. Now we need to talk about the unit. The unit for this problem was liters. Notice where the unit goes. The unit goes after the times 10 to the negative 1. I'm going to put that in a box because that's what you do for teachers. You put your final answers, especially in math, put your final answers in a box. Okay. So all kinds of review with this one. It all started with a simple question of how many liters are equal to 360.0 milliliters. Now, what shall we do next? Let's go back to, we're going to go back to the, what's that thing called? My screen. Alt Shift S, there it goes. It just takes a second. I wonder what this recording is going to be like, because my computer is barely managing to keep up with this. In fact, I'm going to pause the recording for a second. Okay, here are a few more unit conversion tips for you to remember. 98% of the time, you will be starting the conversion process with a value that has only one unit. For example, if the distance to the American Chemical Society conference is 643.7 kilometers from Durham, and you will average 65.3 miles per hour on your trip, how long will it take you to get to the conference? It's algebra. All right, well, two values are mentioned, the 643.7 kilometers and 65.3 miles per hour. The 65.3 value has two units in it. It says that 65.3 miles will be driven with 1 hour of driving. That's 2 units, even though we write them side by side. The 643.7 value is not related to any other unit other than kilometers. Start with 643.7 kilometers. You need to start with that, with the guy that has only 1 unit, because then you know whether to put kilometers on the bottom or miles on the bottom. You determine which way to write your conversion factors, which unit will go on the bottom, based on which unit you start with to cancel out. Don't start with something that has 2 units in it, because then you don't know which one to put on top and bottom. Start with the guy who has only 1 unit. Then, as I said before, once you write a number down, do not write it again. Once 643.7 kilometers is written down, you never use 643.7 again. Oops, I went up. All right. We can actually solve this? Oh, we are. Okay. In unit conversion factors, there should be only 1 unit on top of the fraction and only 1 unit on the bottom. You know when we're going to see this soon? It's when we convert between grams and milliliters using density. Here's the idea. You're going to put either the miles on top and hours on the bottom, or hours on top and miles on the bottom. Don't mix everybody together in 1 unit or 1 fraction, okay? When I write 65.3 miles per hour, the hour has an invisible 1 next to it. So that's where I got these 1s from. In conversion factors, only units that are related to each other can go in the same fraction. The 65.3 miles is related to 1 hour because that is the speed you are driving. 643.7 kilometers has nothing to do with the speed you are driving, so it cannot go in the same fraction with either miles or hours. Just the guys who are related can go together in the same fraction. And it has to be the numbers that make those 2 units equal to each other. I never did solve this problem all the way through, did I? Okay, interesting. I guess I could take a moment to do that. Okay, I guess we'll do that because that's just kind of rude, isn't it? All right, Alt-Shift-S. And we're switching over, hopefully fairly quickly, over to my .cam again. And do I remember these numbers? I hope so. 643.7. And we're driving 65.3, I think it was, miles per hour. Okay, and you'd need one more piece of information for this. We'd need to know how many kilometers and miles it is. Oh, hey, there's one I know off the top of my head. So let's do something fun. So for fun, use the fact that 1 mile, no, I don't know that one. I do, dang, I just remembered it. You know what, we're still gonna do something fun. You know when you see people do 5K races, 5 kilometers, that's actually 3.1 miles. So I'll put 5.0. 5.0 kilometers is the same as 3.1 miles. There's another one that something like 1 mile is the same as 1.6 kilometers. But let's do this one for fun, because I'm kind of tired of working with the number 1. What else do we need to know? Well, I've got kilometers. I can use this conversion to get from kilometers to miles. And then I can go from miles to hours, because the question is, how long? That means how many hours? We're going to start with the guy who has only 1 unit, kilometers, times in a line. I'm going to put kilometers on the bottom. I wasn't told the speed in terms of kilometers. I was told it in terms of miles. So miles will go on top. I need another times in a line because I was asked for time, for hours. So miles will go on the bottom. The guy on top goes on the bottom to cancel out. Then on top, I'll put the hours. This information will come from the definition of miles to kilometers, let's say. Okay, that's something I can look up. This information is coming from the speed. You can do the boom, 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 shakalaka. We'll be left with hours. All right, let's plug in some numbers. Let's see, I made it fun for us so that we would have 5.0 kilometers and 3.1 miles. You might decide to use 1 mile and 1.6 kilometers. And there's going to be another version where there'll be 1 kilometer is point something miles. For my speed, it was 65.3 miles per hour per 1 hour. What are we going to put in the calculator? Let's see. We've got 643.7 times 3.1. I would do times 1, except it's not going to change my values. And now, divided by 5. You could put 0.0 if you want. Divided by 65.3. Divide, divide, divide by anybody on the bottom. Okay? So, and I think that's going to be the code for this one. Divide, divide, divide. So those of you who can't attend the live sessions, that's what you're going to need to share. Anything on the bottom. Okay. What's left? then what we'll do is find out what that is. Grab my handy dandy calculator, and my calculator says, swoop, it says you left me in a weird mode. So I'm going to hit second mode. That's going to help me quit. So usually what we do when we're in person is I help folks with their calculator. If you need help with your calculator, if you wouldn't mind contacting the math resources department using the information I put on the introduction page of Moodle, I would really appreciate it because they can give you a hand with your calculator, and there's lots of different rules for different types of calculators. My calculator is saying that it equals 6.11169, blah, 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 blah. Okay. So before we finish, let's see. The unit we're left with is hours. So this will be hours. And I'm not allowed to put all these down. I'm not allowed to just make up how many I want to do. I have to start at the beginning. At the beginning, it was 643.7. Now, what should we do for this? And we have this. So what I should have done was put 0.2 and 0.0. Let's take a look at what we have. 643.7 is 4 sig figs. The 3.1 and 5.0 are equal to 2 sig figs. The 65.3 miles per hour, that is 3 sig figs. I'm going to be flexible. You may decide that you want to just count this as a definition and work with this one. I'm going to be on the side of caution, and I think I'm just going to stick with 2 significant figures. Either way, I have to start with the 6 point. If it's going to be 2 significant figures, I look at the 1 next door to the 1. That's less than 5, so this will stay 1. If you decide you want to do 3 significant figures, which I'm okay with, then you would have this one would also stay a 1. I'm flexible with this. And in each case, it's going to be hours at the end. And again, put it in a box when you're done. All right, so that was some fun practice. And you got the code to give to me to show that even though you couldn't come to the live session this week, you did watch the video. All right, leave that there for a second, and we're going to do Alt-Shift-S, and I'm going to go back to the PowerPoint presentation as soon as it lets me do it. So I'm going to pause the recording. Oh, nope, here, I think it's ready for us. Nope, pausing the recording. All right, let's get this finished up, shall we? We're on to something new, temperature. Temperature, of course, is a measure of how hot or cold an object is. In fact, we'll learn later, it's really measuring the kinetic energy, so the energy and the movement of all the particles. When you take your temperature in your mouth, you're really just measuring the amount of energy in the moving particles in all the stuff in your mouth. Cool. There are 3 temperature scales that are most commonly used. The ones we use here in America, different from the rest of the world, is degrees Fahrenheit. The rest of the world uses degrees Celsius, and the scientific world uses Kelvin. We're not going to do, I'm going to teach you some calculations with Kelvin, but the only time we're really going to use Kelvin again in this course is when we talk about the gases in chapter 7. So we have a while before we get to that. there are formulas to convert between degrees Celsius and degrees Fahrenheit and vice versa. When I'm given degrees in Celsius and needed to put in Fahrenheit, well, I simply multiply it by 1.8 and add 32. In regular life, I just take the values and multiply by 2 and add 32 because 1.8 is almost 2. The one that's a little trickier is when you need to go from degrees Fahrenheit to degrees Celsius. If you remember your order of operations, you need to take care of the stuff that's in parentheses first. Let's say I have 98 degrees Fahrenheit. First, I will subtract 32 and get 66. And I will make sure that I hit equals and get that answer from the subtraction. Then I divide by 1.8. And so 66 divided by 2-ish, that's about 33. And I think 98 degrees is like 31.7. So that's the way to do it. With the 1.8 and everything, I wouldn't worry too much about significant figures. If your degrees Celsius is in 3 significant figures, your degrees Fahrenheit can be 3 significant figures, and vice versa. Okay. Usually we don't have temperatures that go much more beyond 4. Oh, and you know what? Ignore then with those with the 32. The 32 has an infinite number of decimal places. So again, match your significant figures in the new temperature unit based on the old temperature unit. To convert from degrees Celsius to Kelvin, well, it's not bad. You just add 273. And if you have Kelvin and need to get to degrees Celsius, you subtract 273. The thing that's really cool, degrees Celsius was designed based on water. So water will go from ice to liquid water at 0 degrees Celsius. And then water boils, that physical change from liquid water to gaseous water, that physical change will occur at 100 degrees Celsius. With Kelvin, Kelvin is named after Lord Kelvin, who was the scientist who came up with this, and that has to do with this neat thing called absolute zero. And that's what we see on this thing, that absolute zero and 0 degrees Celsius, 100 degrees Celsius. With our boiling point of water in Fahrenheit, it's random numbers again, 32 degrees Fahrenheit, 212 degrees Fahrenheit. The body temperatures, 98.6. Oh, I went the wrong direction, my bad. It's the same as 37 degrees Celsius. Okay, and one last thing, is it on here? Oh man, it's not on here. Where did I put it? It must be something I write on the board. I'm tired of switching back and forth. There's a little trick, it's in the notes. So I'm just gonna say it. And the trick is, if I give you 3 numbers that are the same, let's say I gave you 0 degrees Fahrenheit, 0 degrees Celsius, 0 degrees, well, 0 Kelvin, there's no degrees. 0 degrees Fahrenheit, 0 degrees Celsius, 0 Kelvin. And I ask you which of the temperatures is the hottest. I want you to go to Kentucky Fried Chicken, because KFC tells you the order for the temperature units. Kelvin is coldest, then Fahrenheit, then Celsius. So the coldest will be 0 Kelvin. The middle temperature will be 0 degrees Fahrenheit, and the warmest temperature will be 0 degrees Celsius. All right, so there you go, Kentucky Fried Chicken for temperature units, if the numbers are all the same. And our last concept that we will do for lab is density. Density is a physical property. It's something that it doesn't matter where my sample's coming from. It doesn't matter how much my sample is. These are values I can look up in a book somewhere or online. Water, for example, has a known density that you're going to have to memorize. So don't worry, it's really easy. And The only thing that affects densities a little bit is temperature. The physical property of density relates the mass of a substance, so kind of like its weight, to its volume, how much space it takes up. Typically, it's common to see it in terms of grams per milliliter or grams per cubic centimeter. If I'm given a mass and a volume, then I use this formula, density equals mass over volume. If I'm given milliliters, I'm given a volume, use the density, whatever density they give you, as your conversion factor. Some people try to do a triangle thing, and I think they kind of do okay with that. Other people just kind of wing it. Do I multiply? Do I divide? People don't get it wrong when they use unit conversion, where they take the milliliters that were given in the question, put milliliters on the bottom, and then whatever the number that came with the density on top. That will be the way I can convert to mass. Okay, and if I'm given a mass and I want it in terms of volume, again, I personally recommend that you start with the unit that goes with grams, the number that goes with grams, times in a line, and take your value for density. Put that number on the bottom with grams, and then the per milliliter of the density, that's 1 milliliter on top. Take your initial number, divide it by the density, and you will have your value in milliliters. I don't know if I did any practice problems with that, but there are some in the textbook if I didn't. Here we go, yay. We're given the density of acetic acid. Acetic acid is the acid that's in vinegar. It's just 5% acetic acid, the rest is water whenever you get a sample of vinegar. And we're told the density is 1.05 grams per milliliter. The density of water is 1 gram per milliliter. So this has a slightly higher density than water. What is the volume of 5.0 grams of acetic acid? Our original quantity, the guy that has only 1 unit, is the 5.0 grams. We want milliliters. I'm not going to use density equals mass over volume because I only use that if you're asking me for density. In this case, we're going to use the density as a conversion factor. Do you see how it has 2 units there? The gram and the milliliter all in one? That screams conversion factor. That's my gateway from grams to milliliters, from mass unit to volume unit. And that reminds me, make sure, I had a student once, we were halfway through the semester, and she didn't realize that grams went with mass and liters went with volume. Please try to remember that sooner than halfway through the course. Well, with density being a conversion factor, it can be written in 2 ways, with grams on top and milliliters on the bottom, or milliliters on top and grams on the bottom. We're going to choose this one where the grams is on the bottom to cancel out the grams in 5.0 grams. So you watch me do several of these. I would have started with 5.0 grams times in a line, put gram on the bottom with a little space in front of it for the density number, put milliliter on top with just a little bit of space in front of it. Recognize that the grams will cancel out, and then you can put in the numbers. Calculator apparently says it's exactly 4.8 milliliters. Not sure. I'm going to go with that because the original number, 5.0, how many significant figures is that? It's 2. The 1.05 has 3. So if we do decide we want to pay attention to that number, it has 3. We need to go with the fewest numbers. 4.8 has 2 significant figures, so our answer is done. Don't forget the unit. I don't like the connect doesn't make you enter units. When you do your connect homework, it's going to have you just putting in numbers, and the units will already be on there. I take off credit for not remembering units. Please remember to include your units. Specific gravity, this is going to be what I call a gimme problem. A gimme problem is one that's so simple you won't have to think about it at all when you do the problem. And here's the neat thing about specific gravity. Because what it does is it's a quantity that compares the density of a substance with the density of water at the same temperature. And since we're just going to use a general value for the density of water as 1, then the specific gravity will be the same as the density of the substance. The only thing that changes is it won't have any units. So the density of water is about 1.00 grams per milliliter at or around room temperature. The units of the numerator, grams per milliliter, cancel out with the units in the denominator, grams per milliliter. They become an invisible 1. So the specific gravity of a substance is equal to its density, but without any unit. Isn't that great? That's why it's a gimme problem. If you're asked for the specific gravity and you've been given the density, just look for the exact same number with no unit. All right, and with that nice, easy end, I believe we've finally reached the end of chapter 1. We have. All right, so I'm going to be putting these up as YouTube videos and then posting them on Moodle, and that's how you watch this, of course. I'll give you links to the PowerPoint presentations and to the, well, it's one presentation, and to the individual handouts. There's also the significant figures handout for you to look at. I'm going to find a chart with conversions between metric units and American units. And I do still owe you another video to do the King Henry died upstairs drinking chocolate milk, to convert that for you. And one more thing, oh, using proportions to cancel out units. I'm going to go ahead and post all this stuff first, though, because I really want you to try to solve the problems this way first, using the factor level method. All right, thanks for watching. See you guys live soon.